For nearly 40 years, one of the most famous, most photographed, most carefully studied planetary systems in the entire sky had been hiding something, not far away, not faint beyond detection. Right there, inside a system astronomers have used as a laboratory for planet formation since the 1980s, a giant world at least twice the mass of Jupiter sat completely unnoticed. It took the James Webb Space Telescope, pointed at that system for an entirely different reason, to accidentally stumble across a signal nobody was looking for, and reveal a planet that had been quietly sitting in plain sight the entire time. This is the real story of Beta Pictoris d, how NASA confirmed its existence almost by accident, and why the method used to find it has scientists excited about an entirely new way of hunting for hidden worlds. To understand why this discovery matters so much, you first need to understand exactly how significant the Beta Pictoris system already was, long before this newest planet ever entered the picture. Beta Pictoris sits about 63 light-years from Earth, and it's a genuinely young star, roughly 23 million years old, practically an infant by stellar standards. That youth, combined with its relative closeness to us, has made it one of the single most valuable systems in all of astronomy for studying exactly how planets form and evolve in their earliest stages. Beta Pictoris was the first star ever found, with a directly imaged disk of dust and debris surrounding it discovered decades ago, and it later became home to one of the very first exoplanets ever directly photographed, a massive world called Beta Pictoris b. A second giant planet, Beta Pictoris c, was confirmed later, giving the system 2 known giant planets and cementing its reputation as one of the best real-world laboratories astronomers have for watching a planetary system while it's still actively taking shape. That reputation is exactly why a team of researchers, led by Aidan Gibbs, a postdoctoral researcher at the University of California, San Diego, pointed the James Webb Space Telescope at Beta Pictoris again. Their actual goal had nothing to do with discovering anything new. They were using Webb's near-infrared spectrograph, specifically its integral field unit, an instrument that captures both an image and a full light spectrum for every single pixel in the frame, to study the atmosphere of Beta Pictoris b, the planet already known to be there. A spectrum, in this context, means splitting incoming light apart into its individual component wavelengths, letting astronomers examine the precise chemical and physical fingerprint of whatever they're observing, rather than simply looking at a picture. While reviewing that data, the team noticed something they weren't expecting. As Gibbs put it afterward, they weren't looking for a new planet. They were trying to understand one they already knew existed, and then, unexpectedly, a telltale signal showed up in the data exactly where nobody had anticipated finding one. Where the researchers had expected to see a smooth, unremarkable spectrum, the kind of signal you'd get from ordinary light simply reflecting off dust, they instead found something with real structure, a pattern of sharp peaks and dips, arranged almost like a barcode, matching the specific absorption signature of carbon monoxide, exactly the kind of chemical fingerprint scientists commonly expect to find in the atmosphere of a genuine giant planet, not in ordinary interplanetary dust. Jean-Baptiste Ruffiot, a research scientist at UC San Diego and principal investigator on the original observation, explained the healthy skepticism that followed that first strange signal. There had been an unexpected bright source of light showing up in the imaging data, he noted, but scientists have learned through hard experience not to trust bright blobs and raw images alone. They can just as easily turn out to be instrumental artifacts, glitches in the telescope's own optics, or oddities in the structure of the surrounding debris disk itself, rather than anything real. What made this case different, and what let the team move quickly from suspicion to confidence, was that they had captured a full spectrum at the exact same time as the image. That gave them a way to check their suspicion almost immediately, rather than waiting for entirely separate follow-up observations. The spectrum data did something else valuable too. It let researchers directly measure the object's radial velocity, essentially how fast it was moving toward or away from the observer, a measurement that reveals genuine orbital motion. When they checked, the object's speed, its position, and its alignment with the system's known debris disk all matched exactly what you'd expect from a real planet genuinely orbiting Beta Pictoris. That evidence let the team rule out the 2 most likely alternative explanations: a distant, unrelated background star happening to sit in the same line of sight, or a brown dwarf, a kind of failed star whose atmosphere might also happen to contain carbon monoxide. Neither fit the data. What remained was a planet. To be certain, the team went further, requesting additional observing time on Webb using what's called Director's Discretionary Time, a special allocation reserved for follow-up work on genuinely significant, time-sensitive findings. Using Webb's mid-infrared instrument for that follow-up, they detected water vapor and methane in the same location, additional atmospheric ingredients that further confirmed this wasn't an artifact or coincidence, and that began revealing real detail about the planet's actual atmospheric chemistry. Separately, an entirely independent research team, led by Ben Sutcliffe at the University of Edinburgh and Marcus Bonze at the European Southern Observatory, used direct imaging observations from the European Southern Observatory's Very Large Telescope, combined with Webb's near-infrared camera, to independently verify that this planet genuinely exists, arriving at the same conclusion through a completely different observational method. That combination of independent confirmation matters enormously in a discovery like this. It's not one team's interpretation of an ambiguous signal. It's multiple, separate lines of evidence gathered using different instruments and different techniques, all converging on the same answer. The planet itself, now officially named Beta Pictoris d, turns out to be a genuine giant, estimated at more than twice the mass of Jupiter, even though it's actually the smallest of the 3 known giant planets now confirmed in the Beta Pictoris system. Computer modeling of its orbit places it roughly 30 astronomical units from its star, a distance comparable to where Neptune sits in our own solar system, making it the widest orbiting of Beta Pictoris's 3 known planets, though it still lies just inside the inner edge of the system's famous debris disk. And that detail, its position relative to the disk, connects to a mystery that had puzzled astronomers studying Beta Pictoris for years, completely independent of the search for new planets. The system's debris disk has a sharply defined inner boundary, along with several other unusual structural features that researchers had struggled to fully explain. Scientists had actually proposed, before this discovery, that an undiscovered planet, roughly matching the mass and orbit Beta Pictoris d turned out to have, might be responsible for gravitationally shaping those exact features, carving out that sharp inner edge and creating the disk's other odd characteristics. Finding Beta Pictoris d doesn't just add a new planet to the count, it hands researchers a genuine physical explanation for architecture in the disk that had been sitting unexplained for years. Here's why this particular discovery has scientists excited about more than just one new planet, though. Beta Pictoris d had gone undetected for so long specifically because it's embedded inside one of the brightest, densest debris disks ever observed anywhere in the sky. Dust within that disk scatters light from the central star in a way that functions almost like fog, making it extremely difficult for standard direct imaging techniques, the kind that simply look for a bright point of reflected light, to reliably separate a genuine planet from the surrounding dust and debris structures. Beta Pictoris d is now recognized as the first planet ever discovered, primarily through this specific method, moderate resolution spectroscopy, identifying a world not by spotting its reflected brightness, but by catching the precise molecular fingerprint of its own atmosphere hidden inside a spectrum, buried in data collected for an entirely different purpose. Ruffio summarized exactly why that distinction matters so much for the future of exoplanet science. A spectrum, he explained, contains an incredible amount of information. You don't simply learn that something is a planet. You immediately start learning about its temperature, its chemistry, and its motion, all from that same single measurement. Traditional direct imaging, by contrast, typically requires extensive additional follow-up work just to move from a promising bright dot to a confirmed planet. Beta Pictoris d skipped much of that intermediate uncertainty entirely, because the very method that found it also handed researchers a head start on understanding what it's actually made of. That capability could prove especially valuable for exactly the kind of environment that hid this planet in the first place. Young star systems still surrounded by bright, messy debris disks, precisely the conditions under which giant planets are actively forming and where conventional imaging methods struggle the most. Gibbs, reflecting on what this discovery adds to an already well-studied system, put it simply. Beta Pictoris has served for decades as a laboratory for understanding how planetary systems form and evolve, and this newest planet gives researchers another piece of that same ongoing story, discovered by a method nobody had specifically set out to test, in a system astronomers thought they already understood. The research team isn't finished with this particular data either. They intend to keep examining Webb's observations of Beta Pictoris d, refining their estimates of its temperature, its full atmospheric composition, and the precise details of its orbit, work that should eventually provide an even more detailed picture of one of the best-known, most extensively studied planetary systems that exists anywhere beyond our own solar system. What makes this story genuinely worth getting excited about isn't just one more planet added to an already impressive count. It's the demonstration, confirmed through multiple independent methods and published in a peer-reviewed journal, that an entirely new way of hunting for hidden worlds actually works. Catching a giant planet that conventional imaging had missed for nearly 4 decades, found it not by looking for its light, but by recognizing the unmistakable chemical signature of its own atmosphere, hiding in data that was never meant to be looking for it at all. If this story got you excited about what else might be hiding in plain sight, hit subscribe, because Webb just proved there's a whole new way to find it.